Hi, my name is Anqi Zheng, and this is my third lab report for the course Physics 2211 on black hole. The purpose of this experiment is to calculate the net force components from observing the motion of a star orbiting a black hole to identify the mass of the black hole. In order to do this, I set up a model on GlowScript, and I could get the results from this model, and is followed by two other discussions, and finally there's a conclusion. There are mainly three fundamental principles used in this experiment. The first one is the momentum principle. The rate of change of momentum could be stated as delta p over delta t equals to delta absolute value of p over delta t times p hat plus absolute value of p times delta p hat over delta t. The second one is Newton's second law, and here the net force could be separated as two parts. The first one is the parallel component, and the second one is perpendicular component. And the third one is Newton's law of universal gravitation, and here we have a formula for the gravitational force, and G is gravitational component. So from these principles, we could get the mass of the black hole. The formula here is F net equals to minus G times the mass of the black hole times the mass of star over squared absolute value of R times R hat. And here we could get a solution of the mass of the black hole, which is absolute value of F net times square absolute value of R over G times M star. So here is the code on GlowScript, and below are the initial conditions given, and you can see that delta t is set to the seconds in 1 day, which is 24 times 60 times 60. These are the first calculations on line 131 and 132. These are the list that is populated with x components and y components of velocity, and in the while loop, these two parts calculate the x and y component of velocity using position data. And here we first calculate the initial and final momentum using velocity and the masses. And on the next part, we calculate the change in velocity and the change in momentum. And on the next line, this calculates the change of momentum over change in time. And for the next part, we use the momentum principle to set dp dt equal to the net force. In the next part, we calculate dp dt parallel. This is the parallel component of the net force, and using the equation F parallel equals to delta absolute value of p over delta t times p hat. And in the next few lines is likely the same as the above, using momentum principle and calculate the perpendicular components. Here is a calculation of the mass of the black hole. Here we have the position of the star and the distance from the black hole to the star, which is R, and on line 195, this formula calculates the black hole's mass using Newton's law of universal gravitation. Here's a visualization of the model. Here the orange arrow represents the total net force, the magenta arrow represents the net force in parallel, and the cyan arrow represents the net force in perpendicular. And next is the video of it. Here we get the result of the mass of the black hole is 2.04263 times E34, and this was calculated using the following formula, which we got using these three fundamental principles. So how is net force different from the rate of change of momentum? From the three equations on the left side, we could see that numerically they are the same, but the net force causes a change in velocity, which also causes a change in momentum. So conceptually, they are different things. And what if the black hole is removed and a different black hole is placed in the same location and the motion of the star remains unchanged? In this case, it would be impossible to determine the mass of the new black hole, since there has to be a change in motion of the star in order to determine a new net force to obtain a different value of mass. So the conclusion is we use Newton's second law and the law of universal gravitation to understand the interactions of the two objects. Thanks for watching.